So, first I also would like to take the opportunity to thank the organizers for giving me the chance to be here and in this very inspiring meeting. The title of my talk is the utility of band theory in strongly correlated electron systems, and I will mainly consider F-electron systems since this is a workshop on F-electron systems. So, brief outline. First, I will give an introduction, which of all facts which you know. Then I will briefly comment on density functional theory as applied to F-electron systems. Then I will show how density functional fails by considering molecular models and comment on standard extensions. And then I will come to the renormalized band methods. First describe the underlying ideas and the applications to heavy fermion systems, and I will briefly present some work in progress and conclude with a summary and an outlook. Now, strongly correlated electron systems, as you know, we are dealing with the problem of interacting electrons in a lattice, and there are two types of tendencies. First, we can gain energy by forming coherent block states and energy bands, and of course there is the other tendency towards localization, which comes from the fact that the electrons are charged particles and they experience Coulomb repulsion. The problem as such is not easily soluble. So far we don't have the general solution. It is a simple solution is available in the limit where we can neglect interaction. And the first treatment is, of course, the free electron systems, which were presented. This solution was presented by Sommerfeld and Bethe. Here we account for the weight character of the electrons, of the fact that they are spin 1/2 fermions, and the ground state then is easily obtained by just filling up the single particle states which have the lowest energy, which leads to, in K-space, to a region which can be characterized in K-space by a region where particles are, where the states are occupied, and this region in K-space is separated by a surface from the unoccupied regions. The low temperature excitations are just created by promoting the particle from the occupied region to a higher energy single particle state, and the characteristic of this ground state is that at low energies we have a linear specific heat and a constant susceptibility according to the fact that we have a single ground state. This forms the basis of the electron theory of metals, and of course band theory just replaces the free electron energies and wave functions by solutions of the Schrödinger equation in the presence of a periodic potential. Of course, this shows that using these solutions of the Schrödinger equation with the periodic potential predicts allowed energy bands, which are separated by energy gaps. The success of this answer is a simple explanation of the existence of metals and insulators. The ground state, however, is built in the same manner out of the single particle states as in the free particle Sommerfeld model. The Fermi surface now may be anisotropic and may have several sheets. Nevertheless, at low temperatures, we still will have a linear specific heat and a constant susceptibility. Now, the problem is, what do we do if we have electrons in partially filled inner shells? And this is a problem which is not, which shows up in the F-electron systems in the discussion whether we have localized or itinerant degrees of freedom. But it's a historic controversy, and this controversy goes back to the time of Slater and Van Vleck. Slater emphasized that the specific heat at low temperatures and the existence of a Fermi surface can be explained only if the electrons are treated as delocalized band states, whereas Van Vleck emphasized that the magnetism requires a localized description. And this dichotomy is a characteristic feature of correlated electrons. There's no simple unique picture which describes the behavior in the entire temperature or energy domain. The same kind of problem shows up in the F electron systems. Here we have a complete analogy between the 4F and the 3D electrons. The main difference here is that the energy and temperature scales are different. We are dealing with much lower temperatures and much lower energies, where we can observe this coherent band-like behavior. The experimental findings are at high temperatures in heavy fermion systems. We have obviously localized F electrons or F electrons which can be described in a localized picture. This is evidenced by well-defined positive effects. At low temperatures, we observe a linear specificity with a large coefficient. The band picture was initially highly controversial for the F electrons. Now, to really describe this on a microscopic basis, we have of course to go beyond the individual particle picture, and it's not useful to talk about states, but we should look at the spectral functions. That means the probability for adding or removing an electron. This here is a cartoon from the Physics Today article by Kotliner and Peter Vollhardt. We know if the interaction is weak or absent, then we have a band. We can have a half-filled band, which is centered at the Fermi energy. As the interaction increases, some side rings appear, and then we get the separation of the spectral function in a coherent peak at low energies and some incoherent side structures. And as when we go beyond a certain 20 limit, only these two upper bands will survive. This is now coming back to the F electrons. We will describe this situation here as an itinerant F electron situation where we have a coherent state, a coherent peak, some coherent states at low energies surviving, whereas here, when there's no spectral wave remaining at the Fermi energy, we would say that the F electrons are localized. The main question is now, can we model the dispersion of this coherent low energy excitations by band theory? Of course, the F electrons now behave like free electrons with a high effective mass. That means they are not really free particles, but we have to go back to the liquid picture, and which postulates a one-to-one correspondence between the excitations of the interacting and the free fermion. This one-to-one correspondence, which just is a way of counting the states, implies that the specific heat still stays linear and we will have a single ground state. The problem, however, is how do we calculate these quasi-particles? Now, first suggestion is always to do density functional theory, which is very successful in determining the electronic properties of, say, simple metals. The ingredient here is we are starting from independent electrons, and the dispersion is determined by effective potentials, which are given by lattice ion and the electron density. It's very successful in predicting ground state properties, and the central quantity is the electron density in the ground state. Now the question is, to which degree is this information sufficient to make predictions about properties of electrons? The important thing here is that to construct the ground state density, we usually use the Kohn-Sham equation. That means the ground state density, which is the fundamental quantity of this theory, is obtained from single particle-like orbitals which which satisfy some type of Schrödinger equation. But of course, these orbitals and the energies, they are auxiliary quantities which are designed to parameterize the ground state energy. The usual assumption is always that these quantities can be interpreted as excitation energies in wave function. The empirical result is this assumption works well for weakly correlated electrons. So the success now in application to F-electron system is the conduction bands in these systems are usually well defined, well described. That's confirmed by Arquette's measurements. The total magnetic moment can be well reproduced, and in many cases also the Fermi surfaces are well reproduced. And the question is this an artifact or a happy coincidence? The typical failures are the scheme is not able to reproduce a paramagnetic state with F wavelengths close to unity and high density of states. Such a state would be unstable and undergo a ferromagnetic transition. And in addition, the low energy peak in the density of states is too wide, so the effective masses of the quasi-particles are underestimated. In addition, the overall bandwidth is too narrow because multiple effects are not included. And how can we understand that despite these failures, the Fermi surfaces are well described? So let's consider how we solve this band structure problem. And an easy way to visualize what's happening is to consider a scattering formulation of the band structure problem, where we consider electron scattering at centers which are sitting at regular lengths. This separates our problem into two parts. First, we have the geometry, which is contained in structure constants, which describe the propagation, the free propagation between the scattering sites, and in addition, the material-specific information which is contained in single-site T matrix. Now, putting everything together, we get eigenvalues equations of this type, where the potential functions, typically which depend on phase shifts, are related to the geometry. So the energy and the K vector, the dispersion, are related. Now, the question is, why does this the density functional scheme of give good Fermi surfaces? And that can be seen, for example, for uranium-based heavy-fermion systems. In these materials, we have a large orbit splitting and only negligible crystal field splitting, so we have 6 J equals 5 half states, which are basically the surfaces of constant energy in K-space, they are parameterized by a set of phase shifts. And here I indicate the conduction electrons by EXC and the F phase shifts by EXX. As the F states are basically equivalent, this is just a single degree of freedom. The Fermi surface itself is now given by a set of phase shifts, but not only the Fermi surface, but also the volume is given by this set of phase shifts. Now the volume of the Fermi surface is fixed by particle number, and so we have a relation between the phase shifts at the Fermi level and so the particle number fixes one phase shift. As the phase shifts of the conduction electrons are well described by density function theory, we see that if all the F phase shifts are equivalent, then also the F phase shift is just fixed by particle number by some kind of generalized Friedel sum rule. This means that if the uranium sites are equivalent, then the Fermi surface does not depend on the detailed description of the 5 F degrees of freedom. It's just given by geometry and particle number. So we would say it's testing the agreement of the measured frontal surface in this situation with the calculated DFT one doesn't tell much about the character of the F surface. Now, let me come to the failure of the density functional theory. This can be seen easily by considering a two-side model where we consider a two-electron state in a model where we have a ligand which is weakly correlated and a strongly correlated F site. And these two sides are coupled by hybridization. So the two-electron ground state just is a singlet which is separated by a small energy from an excited triplet. Here we can solve this model exactly, and since we can solve the model exactly, we can also determine the exact density functional for this model. That means we start from the exact ground state energy, we subtract the potential contribution, we express the F energy in terms of the density distribution, which is characterized by the F valence. And if we do this, we arrive at the density functional for this model, and it has an interesting structure because it has a particle hole symmetry somehow in the lower Hubbard band. Now, going back to the non-interacting reference system, which we need to calculate the kinetic energy in the density functional theory, we can construct, indeed, this kinetic energy to construct the exchange correlation potential. So the energy eigenvalues are determined from an eigenvalue equation, and we choose the potential so as the potential now is this F electron energy. We choose it so as to reproduce the density distribution N, which is quantity, the input quantity. So we see the kinetic energy has a similar structure as the total energy, but it has a conventional particle hole symmetry. From this information, we can construct the exchange correlation potential. It's the exact exchange correlation potential, and what we see if we subtract the Hartree term, that we see that for large Coulomb repulsion U, the exchange correlation potential mainly compensates the Hartree term, and it does not describe the general metabolic effects in the model. Now we go back to the Kohn-Sham equations and we can solve them. What we see here, the general properties now are the exchange correlation potential compensates the Hartree term. We have a normalized F level position, which the F level lies above the ligand. And important thing is that the eigenvalues or excitation energies, they scale with the bare hybridization, not with the normalized hybridization. And that's what we know, what we see from doing density functional calculations. Now the ligand is replaced by conduction bands. The characteristic result always is we have F bands which are shifted to the Fermi level, they are partially occupied. Usually the F count is correct, so we get reasonable Fermi surfaces, but the F band is too wide because the excitation energies scale with the bare hybridization of the normalized. Now, in the case of uranium systems, also the density functional theory plays in another respect. Here we have several F electrons per side, and in principle we have to account not only for this Coulomb interaction, for the diagonal part of the Coulomb interaction, but we also have to account for the interatomic structure, and especially for the mass balance. And what this means is we cannot describe this kind of dual nature effect, this specific correlation effect operative in uranium systems, which can be summarized by this kind of riddle. You know, there's this riddle that a man has to transport a cabbage, a goat, and a wolf across the river. And since these three objects are strongly correlated, it's not possible, or say it's not advisable to take out one of them at random and transport them across the river. But by taking out one of them, one always has to keep in mind what is left behind. In our case, what is left behind are the multiple excitations. So one has to be careful which of these entities can be transported to the other side. So which electron can be transported to the other side, and the selection is done by the multiple effect. That's an effect which is not contained in the upper density of the density matrix. This can be seen also from the two-side model, where we solve the exact solution here in some kind of phase diagram. And here we compare the LDA plus U result. What we see, the LDA plus U can reproduce only high and low spin phases. That means antiferro or ferromagnetic phases. All these complicated compromise intermediate spin phases are absent. And then the degeneracy in the low energy subspace is partially removed by this approximation. In general, the level density is reduced by a factor close to 6, and that's probably the missing enhancement in specificity of the uranium compounds. Now, going beyond EFT, of course, one can construct self-energies using GW or RPA. That's not really will not be very successful in Kondo systems because these schemes do not allow for the Anderson-Purian model in the strong coupling regime. So these schemes should be met with skepticism. So what we did instead is we parameterize the low energy excitations by a phase shift and by a resonant phase shift, which is characterized by a level width and a level precision. Since we do not expect redistribution of charges due to the very weak correlations, we can fix one parameter, so there's a single parameter left, which describes the low energy properties. And in a magnetic field, of course, these quantities have to be calculated as a function of magnetic field. Let's skip this. So with this ansatz, one can describe the Fermi surfaces and the anisotropy in the effective masses. We could predict instabilities of the Fermi liquid and describe the renormalization in the magnetic field and also predict Lifshitz transitions found later. What is wanted, of course, is a determination of the effective masses and, of course, temperature-dependent spectral functions. Just to show that was the prediction of the Fermi surface in the serum between silicon tube, the instability of the spin density wave could be predicted, and then, of course, the effective masses in uranium, palladium, aluminum to calculate directly. Now, let me come to the Fermi surface in the Turkey between silicon tube. That's that's what was predicted from our calculations, and that's what is found in our tests. And of course, these quite well with the experiment. Now, going to higher magnetic fields, of course, we have to calculate the quasi-particles in the magnetic field, and the variation of magnetic field is highly non-trivial. There's, of course, the de-renormalization of the bandwidth. That means the quasi-particles are getting lighter. But in addition, the Zeeman splitting is enhanced, and over the free particle value, and this variation is non-monotonic. And these results here are from an energy calculation. The present calculation uses a renormalized observation theory, which reproduces energy results. So what we find then, using the magnetic field dependent quasi-particle parameters, are some Lifshitz transitions of the Fermi surface, especially of the minority Fermi surface, at well-defined values of the magnetic field. And these Lifshitz transitions were confirmed by transport measurements, there are anomalies in practically all transport properties. This here are the Nielsen data from Jakey's group, and also here these are thermal power measurements from the Europe. Now the question is, what's happening at elevated temperatures, and what's the relevant temperature scale? We saw that we have a thermal surface which includes the F electron at low temperatures, but how does this, how do we get the crossover to the high temperature regime? And so an indicator is an open neck here at the thermal surface, which is missing in the localized the system where we have localized electrons. The message is here now from this paper that we have a very slow crossover, and that this open neck persists to relatively high temperatures, which has implications here for our phase diagram. Now, looking at the phase diagram of the turbine going into silicon 2, we have here, we know that here in high magnetic fields we have a thermal surface which includes the F electrons, and at temperatures, let's say above 1 Kelvin, we also know that the F electrons are low, are band-like electrons. The question is what's happening at this anomaly line, which was interpreted in terms of the breakdown of Kondo effect and the transition from a small to a large thermal surface. And just let me show this here. Now, of course, let me compare this to the renormalized band scheme to the DFT plus DMFT. So the common feature is both schemes use conduction bands from first principles DFT. Both schemes introduce parameters for correlated electrons. But in the renormalized band scheme, we parameterize the low energy peak, and we introduce a single parameter which can be read off from the average specific heat. In DMFT, the high field, the high energy quantities are parameterized. They are the Coulomb energy is parameterized, and then one calculates the low energy. And so, if you want to see more details, I refer to the review article which I wrote for reporting progress in physics. It should appear soon. The outlook is that we try to incorporate microscopic calculation of the X-factor functions with the renormalized perturbation theory, and we use also the RPT to describe time-dependent effects. With this, I would thank you, and looking forward to your questions.
I have a question. So, if I remember correctly from Hughson's stuff, in the large magnetic field, things pretty much became uncorrelated again.
Yeah.
Is that why general expectation, with the way that you're doing the density function theory, it also should work well with that?
I mean, I'm using the Hughson stuff to calculate the single-side T matrix, and in a large magnetic field, it becomes uncorrelated. And we use this fact to derive, like using a renormalization flow to the low energy regime, and extract from this the magnetic field dependent parameters.
Okay, so you do it. So you take it then all the way down to
We
the
take it
zero
down.
field again, just like what he did
Yeah.
as well.
I mean, the magnetic fields where this uncorrelated regime appears that they are unrealistically high.
And then the second question, I mean, and maybe you've already answered it. I had thought that the stuff he was doing was really restricted to the single band Anderson impurity model.
Yeah.
Now you have lots of bands. So how are you, I mean, does that whole machinery generalize to multiple bands?
I mean, in a single impurity model, the only thing which matters is the density of states, the local density of states, and that's kind of. But the main advantage here of the
So you were mapping onto a single impurity?
Right now we are using a single impurity and then solve this spectral function. What's simpler in the electron systems than in the electron systems is that we don't have to worry much about charge transfer because the charge distribution practically is unchanged. If you look at the F electron count in say a charge distribution for a localized F electron compared to a fully hybridized one, it's basically the same because the charges are like. So we don't need this extra cycle to adjust the density. The density will always stay the same. That makes F electron systems much simpler than systems where you have charge fluctuations. Here they are basically flowing apart.
Other questions? Okay, let's thank the speaker again. Move on.